continuing on, and like I said before, we're now going to go back, and this is again exam 3, I guess material would be. So we're going to go back to chapter 7, I think, in the book, and that's going to talk about energy. Which, like I said before, they used to cover that in the previous class, but they put it into this class now. So we're going to go to 7 and talk about energy and thermodynamics. And then we will go forward back to 16 and cover the rest of the thermodynamic sort of properties. All right. So when we talk about energy and sort of the flow of energy, a lot of times, and especially with thermodynamics, we do talk about sort of two sort of aspects of what's going on. And one aspect is the system. And the system really is any part of the world you're interested in. So if you're doing an experiment in a test tube, your system would be the test tube, obviously. And everything outside of your system is the surroundings. So we have, again, a system. We have surroundings. And a lot of what we're going to talk about in this, especially this chapter, is really kind of the flow of energy. And one of the principles that we will talk about is the idea that if something like your system loses a certain amount of energy, then somebody else will pick up that energy. In this case, it would be the surroundings, and really vice versa as well. If the surroundings kind of lose some energy, and probably will enter into the system and it will pick it up. There's really a couple or a few types of systems that we deal with. One's an open system. And in an open system, you can have both the transfer of sort of mass and energy. So like an open beaker, you could take stuff in and out of the beaker. And obviously you could feel if you touch the beaker, it gets hot, it gets cold. So that transfer of energy that's happening. In a closed system, we really don't remove sort of mass, but we can still have that transfer of energy within and out of the system. And in an isolated system, we pretty much have no transfer of anything. Everything is isolated, no mass coming out, no energy being released to the surroundings in that type of system. So again, this is sort of our three systems here. Got kind of like a flask or something in it, could remove mass, can also have that flow of energy in and out. Put a stopper on it, then that's going to prevent stuff from leaving, still having the flow. And then in isolated, we got really no transfer of anything sort of happening. When we talk about energy, it is the capacity to do work, and there is different types of energy. There's chemical energy, as you may be familiar with. There is energy, for example, within, say, chemical bonds. And if we have a bond between two things and we want to break that bond, we have to put energy in to do that. When you do that, everybody gains energy and they can break apart from each other. They have enough energy to do that. One of the words that we know about, hopefully, energy in or energy absorbed, that is what is sometimes referred to, as we will see, as an endothermic process, when heat or energy is basically being absorbed. Also, if you want to kind of make a bond, you got kind of two guys trying to come together here to make a bond. That's actually an exothermic process where energy has to be released. So you got things moving around a lot. So as they release the energy, they kind of slow down and then they can kind of come together. Probably not really like that, but they get them together there and make that bond in that sense. So when we kind of make bonds, for example, it's a exothermic process. Energy is released. There's also potential energy, and that's energy stored based on the relative position of an object. I think was the classic example is like the big giant hill with a giant boulder that looks like it's going to fall over the edge of it. And that boulder has a certain amount of potential energy based on its position. Uh, energy can be transformed to other kinds, and it can transfer to kinetic energy, which is the energy of motion. And if that little rock goes over the hill, it is going to now turn into some kinetic energy. and then it will eventually plop on the ground. Hopefully nobody's underneath it, and it will transfer some energy to the ground or whoever's underneath the boulder. If there happens to be anybody underneath it, they will pick up all that energy, and it will end up in a different state of potential energy at this point at the end of that process. So one of the ideas of the law of conservation of energy is that energy cannot be created nor destroyed, but it can be transformed from one form to the next. And when we think about energy, especially in chemistry, we do think of it oftentimes as sort of a perfect transfer a lot of times. And what I'm talking about is sort of what I said earlier. If somebody is going to release a certain amount of energy, somebody else will be there to pick up that amount of energy. It's going to go somewhere, just not going to disappear or anything like that. And again, a lot of times, it goes out into sort of the surroundings as the energy is being released. Now, when we talk about thermodynamics in terms of energy is the study of the interconversion of heat and other kinds of energy. As we'll talk more about thermodynamics in the later chapter or the next chapter, a lot of times with thermodynamics tries to sort of answer outside of maybe the energy aspect of it is whether or not a reaction will sort of take place. And definitely in the next chapter, we'll talk more about how you kind of use thermodynamics to predict that. But here, we're really talking about sort of energy and the transfer of energy. And energy, along with pressure, temperature, and volume, these are what are referred to as state functions. And when you have state functions, the idea of state functions is it doesn't really matter how you get there. You could take the scenic route, you could take the direct route. What really matters sort of is where you started and where you ended. Those are kind of the two important aspects of it, and kind of your final state and your initial state. So, for example, here, if we look at the potential energy of these hikers, they both started in the exact same position. The red hiker took the scenic route around the mountain, and the blue hiker took kind of the more direct route up the mountain. But really, at this point, they have the same potential energy because where they ended and where they started are basically the same. And that's the most important thing. That's why when we calculate things like delta E, which is the change in energy, it's the final minus initial, change in pressure, also final minus initial, volume, same deal, and temperature. Now, a lot of things when we calculate things that are thermodynamic sort of values, we also look at them in that aspect of sort of final state and initial state. And when we're talking about a chemical reaction where we have sort of reactants that go to products, in terms of a chemical reaction, our products are usually our final state and our reactants are usually our initial state. And a lot of thermodynamic sort of values and properties are calculated just like that. You take up all the thermodynamic properties of the products and you subtract them from all the properties of your reactants. And that gets you your kind of final state minus your initial state. And that's how we calculate a lot of things, including delta H, which has to do with energy and is known as the enthalpy. Any questions on that there? So in terms of energy, there are a bunch of units, and let's just talk about some of the ones that we'll come across. Probably not Newton meters here, but joules, I would say, is a very common unit of energy, abbreviated with a J. Also, kilojoules is another important sort of unit, and the relationship there is there's 1,000 joules in 1 kilojoule in that case. Another relationship that you might have seen last semester, and maybe we'll see it here again. A joule, remember, is equal to a kilogram meter squared second squared. So right around maybe did some root mean velocity, squared velocity. I sometimes use that relationship. And obviously this is not negative, so it's just from PowerPoint there. Now, another sort of units that we don't use all that much in chemistry, but it does pop up occasionally, is calories. And a calorie with a lowercase c is the amount of energy required to raise 1 gram of water by 1 degree Celsius. And calories and kilocalories are also common sort of energy units that are sometimes used. Same sort of relationship. There's 1,000 little calories in 1 kilocalorie. I say lowercase c here because there is also sometimes nutritional calorie, which is capital C, and that is usually a nutritional calorie. One nutritional calorie is actually 1,000 of the little calories, and that is equal to 1 kilocalorie in that case. So there's also nutritional calories, which again are different actually than lowercase c calories. Um, and usually, if we use calories in sort of calculations, it is the lowercase sort of c. The relationship between those two is 1 calorie is 4.184 joules. Maybe not from last class, but the previous class, you may recognize that number. That is the specific heat capacity of liquid water, and the conversion between joules and calorie in that case is 4.184 joules. One way we use energy is to change the temperature of a substance. Obviously, if we take ice to liquid, we have to put energy in, and that will sort of require a change in temperature that occurs. Now, thermal energy is different than actual temperature, but thermal energy is the energy associated with the random motion of atoms and molecules. And the greater the amount of thermal energy there is, has to do with how many molecules or atoms there are. So the more matter you have, the greater the thermal energy will be. And again, the distinction between thermal energy and temperature is, for example, if you had a cup of coffee that was 70 degrees Celsius and a bathtub of water that's 40 degrees Celsius, the bathtub of water here would actually have the greater thermal energy because there is definitely a lot more water molecules in that than your cup of coffee, even though it has a lower temperature than your cup of coffee. That is a higher temperature. So temperature is a measure of sort of energy transfer. But again, here the idea is if you try to heat up, say, a cup of coffee or water's worth of coffee cup, it probably will heat faster, right, and get to a higher temperature than if you tried to heat up that bathtub of water because there's just more water molecules present. And, you know, if you take a big giant pot of water you're trying to boil pasta in, it takes a while for that to heat up, right? It just doesn't jump to like 100 degrees really quickly. It takes a while to build enough energy to do so. And that actually is something we're going to talk about a little bit later on in the chapter. And again, something maybe you remember, and that is specific heat capacity. So it takes a certain amount of energy to change 1 gram of a substance by 1 degree Celsius. And for water, you know, it takes a lot more. So when you have more, it takes more energy to put in there to get it to a higher temperature. But we can use temperature to understand what's happening in terms of the flow of energy. So if we have our temperature and the temperature starts to increase as a result of something that's happening, which is, say, a substance temperature increases when you do a reaction, we know that that substance is gaining energy, right? That is an idea of an endothermic process for it. As it's absorbing energy, the result of that is the temperature should rise. If somebody is releasing energy, we would see their temperature start to decrease if they are releasing energy. And if again the temperature goes up, they are gaining energy. So we definitely can use temperature as sort of a measure of, you know, what's happening in terms of the flow of energy in a substance, right? By the way, heat and energy transfers from cold to hot, hot to cold, goes from hot to cold, right? So heat flows from hot to cold, hotter object gets colder, colder object warms up. And maybe if they're in an insulated container, they meet somewhere in the middle in terms of their temperature. But we always have the flow from hot to cold. And that is what we see in terms of temperature as well. Again, if somebody's releasing that energy, their temperature should be dropping, and vice versa on the next one if they're gaining it. So as we talked about here, that flow of energy is the heat, and that is the transfer of thermal energy by two bodies that are opposite temperatures, and again, flowing from hot to cold. An exothermic process is a process where energy is released, and again, striking a match is an example of that, lighting a Bunsen burner, right? You put your hand near it, you can feel the heat and energy coming off to the surroundings. An endothermic process is a process where heat and energy is absorbed, and somebody absorbs energy. Like if we take an ice cube out, just put it on the table without you doing anything, it starts to melt because it's going to absorb the heat and energy from the surrounding air, right? Because the air is warmer than the ice cube that you just took out of the freezer. So the flow of energy is going to go into the ice cube and it's going to cause it to start to melt. Also, why when you make ice, I don't know if people make ice anymore, but if you put water and you put it in your freezer, that is why when you put water into your freezer, you end up with ice. Because when you put the water into the freezer, the water is at room temperature, which is hotter than the freezer temperature. All the energy from the water, liquid water, is going to leave, and that's going to cause it now to go into the solid state and freeze at that point, and you get some ice cubes in that flow. So again, always flowing from hot to cold in that process. That's the same idea as when you use like warming things for your hands, right? You crack it, does a reaction, exothermic reaction in your hand. Your hand is endothermic, picking up all that heat and energy, and your hand feels warm when you do that. Or if you have an ice pack, opposite thing, it draws all the heat and energy out of your hand, and you start to feel really cold in that situation. So let's take a look at some energy diagrams, and these are some typical energy diagrams of an exothermic process and an endothermic process. And on the left here, we have an exothermic process, and on the right, we have an endothermic process. These are our reactants, and these are our products down here. And the only way that our reactants can get down in terms of energy to our products is energy has to be released in this case. So energy is going to be given off in this case to do that. As it goes through this process, and as hopefully you know, when you have a chemical reaction, the only thing that happens is we make bonds, and we also break bonds. We kind of break bonds first, I guess, and then make bonds. So all you're doing, right, is breaking bonds and making new bonds. We don't change any elements or anything like that. So it's all about electrons and breaking those bonds. And that is what happens as these reactants are heading through this reaction. They are starting to break their bonds. So as they are climbing this hill of energy here, as they're moving in this direction, they're starting to break bonds, and they're actually starting to make some bonds as they're moving up this hill of energy. This hill of energy actually has a specific name, and from where the reactants start to kind of the peak of the energy, that hill is what is known as the activation energy. And that is sometimes abbreviated E of A. That is the minimum amount of energy that's required for a reaction to take place. So for a chemical reaction to take place, two things has to happen. Things need to hit each other, and they actually have to collide with each other in the correct orientation, the correct spot, like the active spot in both parts. And they also have to hit each other with the right amount of energy, and that is the activation energy to get up and over the hill. When they get to the very top of the hill, which is the highest point in the energy spot, this is what is sometimes referred to as a transition state. And when you reach the transition state in a reaction, you typically have what is sometimes referred to as a transition state complex, or some people call it an activated complex. This is a very unstable sort of compound. This is something that has partially broken bonds and partially made bonds. So it's very, very unstable because of that. And what happens is typically those guys are sometimes abbreviated with a little symbol when they get up there, just a little kind of symbol type thing. And what happens is because they have partially made bonds, partially broken bonds, and that is really the peak of energy in a reaction. And one thing that we hopefully know about energy and chemistry is we do not want high energy. That's an unstable situation. Everything that we do usually is to kind of lower the overall energy, try to get to a much better state in terms of energy. So what happens is because this is very high in energy, it will very quickly usually kind of come down the hill to the other side and really make products at that point. And for a lot of reactions, that sort of transition state complex is usually very hard to isolate because it does not stay around a very long time because it'll just kind of has those partially made bonds, partially broken bonds will basically drop right down. Over here on the other side, we have, again, our reactants. Over here, we have our products. And the difference here is our reactants are actually lower in energy than our products. And the only way for our reactants to get to our products is energy has to be kind of put into this case. And that's going to be an endothermic type process. We also have our activation energy, as you can see here to the top. And the same idea as we come down. Now, how do we know, if this is exothermic or endothermic? One of the ways, and we're going to talk about in this chapter, that we sort of represent energy in a reaction, and you probably have seen it before, is what is known as delta H, which is the change in enthalpy. It is a fancy way of saying the heat involved in a chemical reaction, how much is absorbed or released. And the way that we calculate the delta H for a reaction is we take the delta H of our products minus the delta H of our reactants. So again, our products being our final state, our reactants being our initial state. So we're taking the difference between final and initial state in this case. So if we look at these sort of energy diagrams here, maybe I'll clear out some of this here. And if we look at the difference between where the reactants started in energy and where the products ended in energy, that is, as the diagram shows, really the delta H of the reaction or the heat of a reaction. And if we were to calculate in the case of a exothermic process, the delta H of a reaction for exothermic, we just look at the graph, our reactants are in higher energy than our products, which is in lower energy. So what you would essentially be doing is taking a smaller number minus a larger number. And typically when you take a smaller number minus a larger number, you end up with a negative number. And that is why when we calculate the delta H or see a delta H for a reaction and it's negative, it indicates it is a exothermic process. And the same idea over here, if we did our delta H of our reaction for our endothermic, our reactants are lower in energy than our products. So when we take products minus reactants, we're going to take a larger number minus a smaller number. And that's going to yield us a positive value for delta H. So again, when you see a positive value for delta H, and to be truthfully honest with you, you see a positive value for any energy value, that is usually an endothermic type process. If you see a negative value for energy, it's usually an exothermic type process, which is why it's really important when you do calculations, especially with energy, that you just don't disregard the negative sign if you get it. And if you do get a negative value for energy, it is telling people that you are dealing with a exothermic reaction versus an endothermic reaction. Any questions on that there? By the way, the activation energy, which is the hill the reactants has to climb to get to the other side, is a very big factor in how fast or slow a reaction takes place. If you have a really big activation energy hill that people has to climb to get to the other side, you most likely will have a slower reaction than if you had a smaller activation energy hill for people to climb. If you just think about it, right? If you had to climb a big giant hill to get to the other side, not very many people will go want to do that, perhaps, right? But if you had just a really small, like speed bump type hill, everybody's not going to have a problem to get to the other side. Most people could get to their side a lot quicker and stuff like that. So that activation energy hill is something that determines how fast or slow a reaction takes place, which is kinetics. And you can see just in general here, our endothermic reaction has a much bigger, usually activation energy hill to climb to the other side. That's why overall we need to kind of put energy in this system to kind of help people get up and over to the other side. As you may be familiar with, one of the ways you can speed up a chemical reaction is to add a catalyst. And if you add a catalyst, it is again not a reactant. It is not a product. And it does not get used up. It is there really, again, just to find a more efficient way for that reaction to take place, a more efficient pathway for that reaction to take place. And by doing so, it's able to speed up the chemical reaction in most cases. And the way it's able to do that is, again, by sort of finding an alternative pathway, a more efficient pathway. It ultimately will actually lower the activation energy hill. So this would be more like a catalyzed with a catalyst reaction. And because it lowers the activation here by finding this more efficient pathway, it allows more reactants to get to the other side, and thus usually will speed up the reaction because more reactants will have enough energy to kind of get up and over to the other side. Again, because not all collisions, even though two things come together and hit each other, will result in products actually being formed. Any questions on any of that there? Yeah. So here again, we have our H2 and O2 making water, going to release energy, and our decomposition of mercury 2 oxide going to make our products here, which are higher in energy. Now, when we talk about heat and energy, and we touched upon this a little bit with Le Chatelier's principle, we do think of exothermic as, again, in a lot of cases, being a product of heat and energy. So just like we talked about in Le Chatelier's principle, you will sometimes see, perhaps not too much in this type of class, but sometimes people will write an energy sort of component into a chemical equation. And if you do, you would think of it as a product or be on the product side, like is being given off in an exothermic. Or on the reactant side, if it is an endothermic process, heat and energy can be written into the equation as a reactant. And that is the way we treat heat and energy, especially when we talk about Le Chatelier's principle, if we have a endothermic or exothermic. Again, in most cases at this level of chemistry, they usually don't write it into the reaction. They will just give you a delta H value that's either negative or positive, and that is typically how they represent it being endothermic or exothermic. Any questions on that there? So as we talked about before, in this case, if we have hot water next to cold water in an isolated insulated container, all the energy is going to kind of move from, again, our hot to our cold. The result of that is our cold water is going to pick up the energy. The temperature of the cold water should go up. The hot water is going to release the energy, so its temperature is going to start to go down. And eventually we will see it sort of equilibrate to probably about halfway the temperature between the two when you do the average. So let's talk a little about enthalpy more officially here. So enthalpy, again, is, as I mentioned, it's a way we most commonly in chemistry express whether or not heat is being absorbed or released by a reaction. And again, that is the delta H. And the way that we calculate it, again, is for a reaction, we take all the delta H's of our products and we subtract from all the delta H's of our reactants. Where do we get these delta H values? We typically get it from a table, a thermodynamic table, which you have in your book. And usually that table will have all the thermodynamic values in it, H's, S's, and G's, which we'll talk about in the previous next chapter. But usually you could look up and find what is referred to as the delta H of F or the delta H of formation. And these are basically enthalpy values for everything. Typically speaking, delta H of formation values are 0 kilojoules for anything that's in a standard state uncombined. So if you have like a metal by itself, it's going to have a delta H of 0. If you got O2, it's going to be 0. That's naturally how it comes. So usually most things for delta H's, if it is something that is sort of in a standard state uncombined, how it naturally comes by itself, usually will have a delta H value when you look it up in a table of 0. So we could calculate by really adding up all of our products and all of our reactants and calculate our delta H. And again, if we end up with a negative value, that'll be a exothermic reaction. And if we end up with a positive value, it'll be an endothermic reaction. So for example, if we have this reaction here, 2A plus 3B goes to 4C. And what we would do is we would go to our table and we would find A, B, and C, and we'll have our delta H of formation. I'll just make up some numbers, 20 kilojoules minus 20 minus 100 kilojoules, and why not a 60 kilojoules for that one? So we would go to the table, and it's really important when you do sort of reference a thermodynamic table for this chapter and the next chapter as well. It's really important that when you look up the substance, you find the substance that you're interested in, but it's also most important that you find it in the correct state. So if it's a aqueous, you want to find it as an aqueous. If it's a gas, you want to make sure you look up the gas value. I would say water is a very common one people screw up on because you just go to the table, find the first one that says H2O, and it may be gas, maybe liquid. It may not really be in the correct state that you want. You want to make sure it is in the correct state, not only just the right object or substance. When we do this, we're going to calculate this. The delta H of the reaction, again, is going to be the delta H of our products minus the delta H of our reactants. Now, one of the things that we do have to take into account when we calculate this is actually the coefficients. And these coefficients, as you know, are moles of each of these things. And when you look it up in the table, these are really kilojoules per mole, most of these. And we do need to not only find what we're looking for, but we do have to multiply it by the coefficient in the balance equation. So if we were going to do this, we would calculate the delta H for this reaction by taking our products, which is our C. We're going to take 4 because of the coefficient, times it by the value of C we would find in our table, which would be 60 kilojoules per mole. And that is all of our products. We then will subtract all of our reactants, which obviously here we have 2A, so we have to take 2 times the value of A that we would find in the table, minus 20 kilojoules per mole. We would then add it to our other reactant, which is B, and B does have a coefficient of 3. So I'm just going to go underneath it, 3 times the value of B in our table, which is minus 100 kilojoules per mole. And that is going to give us our delta H for this reaction. So let us calculate it here in my made up one to see how bad I did. So 4 times 60 minus 2 times minus 20 plus 3 times negative 100. Going to get us, looks like 580 kilojoules in this case, if I calculate that right. That would tell us in this particular reaction that I just made up, is it exothermic or endothermic? This one should be. It is endothermic, and all you have to look at is the delta H value. It's positive, so that tells you overall this reaction is absorbing energy in this process. Any questions on how to do that there? All right, so why don't you try one here again is typically what the table looks like where you would find those values. So calculate the delta H for this reaction and see what you come up with. All right, so let's take a look at it. So obviously, if this was not provided for you, you just have to go to the table in the back of the book. It's usually where you can find these tables and look them up. And as I mentioned before, you can see things in their standard state do have values of 0, and that's typical for delta H values. And again, they're usually referred to as the delta H of F or delta H of formation sort of values. Here again, we're just going to do our products minus our reactants. So again, our products minus our reactants, final state minus initial state. So on our product side there, we got two sodium hydroxides. So we're going to go 2 times the value of sodium hydroxide minus 470 plus our other product, which is H2, which is a value of 0. So that's not too bad. That takes care of all of our products. We'll now do our reactants, and we got 2 times sodium, which is also 0. Not too bad there. Plus our 2 waters, which again is our liquid water, so minus 286 kilojoules in this mole. And that takes care of all of our reactants. So we do that there, 2 times minus 470. And then we're going to basically subtract it from 2 times negative 286. That's going to yield us a negative 368 kilojoules in this case. Question on the calculation here. This one would then be exothermic, as we have a negative value here for our delta H in this reaction. So overall energy being released in this case. Any questions on that there? All right, and again, look it up in the table if it's not given to you. So we have 16 of the COs, which are over here. So it's going to be 16 times minus 110, I think. We're going to add it with our other product, which is 18 waters. So 18 times the value there of water in the table, minus 286. That takes care of all of our products. We'll do the same thing for our reactants. We got 2 times our C8H18, and that has a value of minus 208, plus 25 times a value of 0 for our O2. And if we do that there, we got 16 times negative 110 plus 18 times negative 286. We're then going to subtract it from basically 2 times negative 208. It's going to give us a negative 6492 kilojoules. Once again, here going to be exothermic, as we have a negative value here. Any questions on how to calculate delta H of a reaction? So basically, typically these type of problems, you're just given a reaction and they're like, what is the delta H? And that's a good sign to go to find a table and look up the values and do products minus reactants. Any questions on that there? All right, we'll skip that one. So another sort of aspect of these type of reactions is this is typically what you would be given in a reaction a lot of times is you're given the reaction here. We got a combustion reaction here of propane, and it has a delta H of minus 2221 kilojoules. And obviously, this is going to be an exothermic process here, like a lot of combustion reactions are, since they give off heat and energy and flames, and we have a negative delta H. But in this case, we want to assume that all the heat comes from the combustion of propane, which is the C3H8. We want to calculate the delta H when 0.113 moles of propane are burned in the oxygen here. Now, one of the things that you could do with an equation, if you have like the delta H sort of value given to you, is you could write what are referred to as thermochemical sort of conversions. So just like we could do in stoichiometry a mole-to-mole conversion between everybody, where we could use the coefficients and go for 1 mole propane, I would react it with 5 moles of O2. Our 1 mole of propane will give me 4 moles of H2O. We could do our mole-to-mole relationship We also could do a mole to energy relationship that we see from the equation. So for example, here, for every 1 mole of propane, we get out negative 2,221 kilojoules of energy. That actually gives us, much like in stoichiometry, two conversion factors that we could use. That's kind of a mole and energy conversion factor rolled up into one. We could say 1 mole of C3H8 over minus 2,221 kilojoules, or minus 2,221 kilojoules over 1 mole of propane. So we could kind of get this equality from the equation, and we could get these couple conversion factors that we could use. We could obviously do this for anybody in that equation. We could say for 5 moles of O2, we would get this much energy coming out. So we can do that relationship with anybody, just like you could kind of do it with stoichiometry from anybody in the equation. You could do this energy relationship. So in this particular equation, our problem, what we're looking for is what is the energy, or delta H, when we only take 0.113 moles of propane. So we could do this just like almost a stoichiometry problem, 0.113 moles of propane. We could choose our proper conversion factor where opposites cancel. So we would want the moles of propane on the bottom. And, whoops, where'd it go? There it is. So we'll go this way here. Actually, let me just do it down here. 0.113 moles of propane. A mole of propane gives me 2,221 negative kilojoules of energy. So if I go 0.113 times negative 2,221, we see that we would get minus 251 kilojoules of energy released. 1 mole of propane gives us 2,200. 0.1 of a mole will only give us minus 251 kilojoules of energy release. So you can do sort of a stoichiometry relationship between moles and energy in an equation if you have a delta H to figure it out. By the way, if we were not given moles but we were given grams, we could also just convert grams to moles using the molar mass, right? And use that relationship to do so. Any questions on that there? So that is, again, something that is sometimes used with these sort of energy type equations, that sort of energy mole relationship. The next type of energy we're going to talk about, our heat, is specific heat capacity. And specific heat capacity is the amount of energy that's required to raise 1 gram of a substance by 1 degree Celsius. It is basically the same definition as a calorie, except calorie is about water, and this is about any substance. And there is a specific heat equation that is used, and that is what is there. And it is Q is equal to ms delta T. Now, Q is heat, our energy, but usually heat. And the units that are usually associated with Q is joules or calories. And I would say in most cases, probably for you, joules is usually what you see. M is mass here. And the units of mass is in grams. Now, S is the specific heat capacity. And S has units of joules per gram per degree Celsius, or calories per gram per degree Celsius. That is actually the definition of specific heat capacity, which is the amount of energy, which is joules per gram of a substance to raise it by 1 degree Celsius. So those are why it has all three units. People oftentimes will get Q and S confused or backwards. So the one that has all three units is the specific heat capacity, or S, and the one that is one unit is just Q. Now, probably the most important thing here is delta T, and that is the change in temperature, and that is our final temperature minus our initial temperature. And this is one of the few things in chemistry that we actually keep in degrees Celsius. And the reason we keep it in degrees Celsius is because typically our specific heat capacities are in degrees Celsius. So we do not convert this to Kelvin typically unless our specific heat capacity is in Kelvin. But usually physics says that Kelvin. But here in chemistry, we actually still leave it in Celsius. Now, when you look at this equation, especially the S, which is specific heat capacity, some people will use C to represent specific heat capacity in that formula, or some people in some books will use SH to represent specific heat capacity. So sometimes you will see a couple of different letters, sometimes used in different places to represent specific heat capacity. I personally use S pretty much always, and a lot of places do, but some places will use C for specific heat capacity, and I've even seen books use SH sometimes for it as well in that formula. Um, what is the deal with Q? Q can be a positive number, RQ can be a negative number, and much like energy, it tells you the same thing. If you end up with a positive value for Q, you are rolling with an endothermic process. If you end up with a negative value for Q, you are rolling with an exothermic process. Now, the only thing that is in this equation that can become negative is actually the change in temperature part. Everything else is going to be a positive number. Mass is going to be positive. Specific heat capacity will be positive. So it is really important that you always do final temperature minus initial temperature, and that will give you a negative sign if you need one, and a positive sign if you need one of those as well. Sometimes people in classes, especially earlier classes, are taught just take the difference of the temperature. It doesn't really matter. But it does matter. So you do want to do final mass initial, so you will end up with a negative value if you need it, or again, a positive value if you end up with it. So you should always try to make sure you do that so you end up with the right thing. Now, the specific heat capacity of liquid water is down there. So the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. That is also the conversion factor between calories and joules. Or if you're doing calories, it is 1 calorie per gram per degree Celsius. By the way, if you're not doing liquid water, but you're doing ice, which is solid water, or you're doing steam, which is gas version of water, the specific heat capacity for those things are different. They're more like 2 joules per gram per degree Celsius. So they are different values if it's not liquid. So if you happen to come across a problem where you're not doing liquid water, you do want to use a different value than that. You want to go look it up for the proper state. Any questions on that there? Specific heat capacity tells us that if I have a large specific heat capacity, it's going to take more energy, right, to raise the gram of 1 degree by 1 degree Celsius. That takes us back to our liquid water bathtub example we saw earlier in our cup of coffee. In the cup of coffee, there's much less grams, right? So it's not going to take long to raise that much in terms of energy and get the temperature to change. But when you have a lot bigger amount of water there, it's going to take longer to see the temperature range. Liquid water has a relatively high specific heat capacity. And that is why, right, people get a little worried when the ocean water goes up like a half a whatever degree of temperature, right? Because we think about how much water there is, just to move it up that much is a lot of energy to get it to change. Here's a table similar to one you're finding in your book. And like I said before, you can see here ice is 2.03 and steam, which is the gas version of water, is 2. So it does change with different states as to what you're using. But for the most part, liquid water is the one you come across the most. So that 4.184 is usually a number that you will use a lot. All right, so let's take a look here. Determine the amount of energy as heat that's required to raise the temperature of 10 grams of aluminum. Specific heat capacity of aluminum, 0.89 joules per gram per degree Celsius from 25 to 58. Give your answer both in here. We're looking for heat, which is Q. We have the mass given to us, which is 10 grams. We got our specific heat capacity given to us, 0.89 joules per gram per degree Celsius. We have our initial temperature, 25 degrees, and our final temperature, 58 degrees Celsius. So we really have everything we need to go into our formula here. So we'll just plug and chug into here. We got 10 grams. We have our 0.89 joules per gram per degree Celsius. Again, we want to go final temperature, which is 58 in the 25 times 0.89 times 10, about 293.7 joules. I can't write 7 today either. Or a 290 in that case with the same conversation there, I suppose. Yes. Question on that there. 293.7 joules. We want to convert to calories, so there is 4.184 joules is 1 calorie. Joules going to cancel. That's going to get us there. 4.184. About a 70 calories in this case. Or if you used a rounded number, maybe 71. Any questions on that one there? This is a endothermic process. Our Q is positive. We also see that by our temperature, right? Our temperature went up, right? So it gained energy. It results in the temperature going from 25 to 58 and increasing. All right, let's try another one here. Maybe I'll do better on this one. 294 joules of heat is transferred to 10 grams of silver, 25 degrees Celsius. What is going to be our final temperature if the specific heat capacity of silver is 0.24 joules per gram per degree Celsius? Joules is our Q. We got our mass of 10 grams. We got our initial temperature of 25, not 8. There we go. We're looking for our final temperature here, and we have our specific heat capacity, 0.24 joules per gram per degree Celsius. So going into our equation here, in this case, we could actually solve for our delta T by dividing that to the other side. So that will give us delta T is equal to Q divided by MS. And popping in our numbers here, 294 joules divided by our mass of 10 grams. And our specific heat capacity, 0.24 joules per gram per degree Celsius. The joules will cancel, the grams will cancel, going to leave us degrees Celsius when it's all said and done. 294 divided by 10 and divided by 0.24. Going to get us a 122.5 degrees Celsius. Remember, though, that this is not the answer because this is the change in temperature, and that the change in temperature is equal to our final temperature minus our initial. So in this case, we got 122.5 equals our final temperature minus our initial, which was 25. We're going to add that to the other side. And that will get us there, 122.5 plus a 25. Going to give us a final temperature of about 147.5 degrees Celsius in this case, which did go up in this case as we would expect, since our Q is a positive number, so it is absorbing energy in this case, and we should see the temperature go upwards. Yeah. Any questions on that there? Now, you could do these sort of specific heat sort of experiments very simply with a couple coffee cups and a thermometer, and all you have to do is just follow the change in temperature of the water, basically. And you could even do this a lot to follow reactions and solutions, because the main part of solutions usually is water, so you can use specific heat capacity. So it's a very sort of simple process that you could do to figure out how much energy is being transferred or not. Let's talk a little bit about, though, about a situation that does occur. Let's just say, for example, we did have some water here. And let's just say we had, we'll go with 105 grams of water, initial temperature 25 degrees Celsius. And let's just say we had a piece of metal here. And let's just say the mass of the metal, it was, we'll go with 75 grams. We'll have an initial temperature. We heated it up to 99 degrees Celsius. And if I take this piece of metal and I throw it into my water, carefully, I suppose, the transfer of energy in this case is going to go in which direction? Will it go from the water to the metal or the metal to the water in this case? Which way should the energy flow or heat? Heat should flow from the metal, which is hotter, to the water, which is cooler. So for our metal, it's going to release its energy into the water. That's going to pick up the energy. So for our metal, it's going to be exothermic. For our water, it's going to be endothermic as it's picking up that heat and energy. Now, if you threw a piece of metal into some water that was hot, the metal would eventually cool down in this situation because it's hotter, and it will eventually come to rest at the same temperature as the water does at the end. So let's just say the water's final temperature went up to 28 degrees Celsius. That means that the final temperature of the metal, because it's sitting in that 28 degrees water, will also equilibrate to the same temperature. Now, a couple other things that we do know, if we wanted to know the specific heat capacity of the metal in this case, we could actually use the information for the water to help us do that. We always know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. So if we wanted to, we could use our specific heat equation for the water, and in this case, really figure out how much energy or heat that the water gained. And that would be, in this case, 105 grams, our specific heat capacity of liquid water. And our final temperature of the water, which was 28, minus our initial, which was 25 degrees Celsius. And let's see how bad I did making up numbers here. That means this water is going to gain somewhere in the ballpark of 1,318 joules of energy, as the grams in Celsius will cancel in this case. First off, any questions on that there? So the water here ends up with a positive Q, which makes sense because, again, it's colder, so it's going to absorb all that heat and energy from the hot piece of metal that you dropped in there. Now, can we figure out what happens to the metal? So earlier we talked about the idea that if somebody loses a certain amount of energy, somebody else has to gain that amount of energy. And in this case, the water gained all that energy from one source, which is the metal. And the relationship in that is Q of the metal will equal negative Q of the water. So for the metal, in terms of its heat and energy that it lost and gave away, would actually be negative 1318 joules, as that is a exothermic process for it. It is the same amount of energy that was transferred. Again, just for one thing, it's exothermic. For the other, it is endothermic, and the signs are different. By using that information, we now have for our metal everything that we need except for the specific heat capacity. And we can now go back into our specific heat equation one more time and do it for our metal in this case. And we're going to solve for the specific heat capacity, which means we're going to take both of these guys and divide it to the other side. And that will give us S of the metal is equal to Q of the metal divided by M and delta T for our metal. So putting in our numbers here for our metal, we have negative 1318 joules. divided by the mass of the metal, which is 75 grams. And now the important part when I get to my metal is, again, I want to do, for a change in temperature, final minus initial. Final temperature to metal is 28 degrees. Initial temperature is 99 degrees. The importance of making sure I do it this way is that number is going to end up being a negative number. And that negative number you get there will take away the negative that we have here, and we are back to a positive number for our specific heat capacity. So again, that's an important little part there. 1318 divided by 75 divided by, what I got there, 28 minus 99. That is going to give me a specific heat capacity for my metal of 0.25. Not too bad. None of the units cancel here, so joules per gram per degree Celsius, all the units will remain. So this is a very common way where we kind of use what happens with water, because we know specific heat capacity of liquid water. And by knowing how water changes, we can figure out how much energy water absorbed in this case, and that will tell us how much energy was released by the metal. By the way, it is possible that if I took a piece of metal out of the freezer and threw it into my room temperature water, which way would the energy transfer? In that case, the energy would transfer from the water to the metal, because the water is warmer than the metal. So the energy would go that way. It would be opposite. So again, you always want to keep in mind that transfer from hot to cold, because it could be going the other way. In that case, the water would actually be exothermic. The metal would be endothermic. It would be absorbing all that. Any questions on that there? On, as we were just talking about there at the end, we have this sort of heat transfer, this perfect sort of transfer of energy from one object to the next. And when you have that situation, basically the total heat should equal zero when you add how much heat was gained by the water to how much heat was released by the metal, and it should equal zero. Again, you can kind of set it equal to zero, but you do have to distribute that negative on one side or the other when you do it. Sometimes it's easier to do this calculation like we just did in the previous one, kind of two individual calculations rather than plug it in here. So why don't you try one here? A 110-gram sample of a metal at 55 degrees Celsius, or 55.5 degrees Celsius, raises the temperature of 150 milliliters of water from 23 to 25.5 degrees Celsius. What is the specific heat capacity of the metal in this case? So give it a go, see what you come up with here. Okay, so let's take a look. So it's a similar situation we have in terms of a metal here. We have the mass of it, which is 110 grams. We have the initial temperature of the metal, which is 55.5 degrees Celsius. We do have some water, and we have 150 milliliters of the water, and it has an initial temperature of 23 degrees and a final temperature of 25.5 degrees. And we want to determine the specific heat capacity of our metal. Once again, we're going to toss the metal in. And in this situation, again, the metal is a hotter temperature than the water. So the metal should definitely release its energy to the water in this situation. And that means that eventually our metal will come to rest at the same final temperature as the water. So again, for our metal, we know it should be the same in this situation. So just like before, we can kind of really follow what's going on with the water to understand what's happening with the metal. So a couple things we know about water always: liquid water, specific heat capacity, 4.184 joules per gram per degree Celsius. We don't have the mass, but we do have the volume. And also something we should know about water is the density of water. So we could actually use the density of water, which is 1 gram per milliliter. The milliliters will cancel, and we'll actually end up with 150 grams of water in this particular case. So just like in the previous example there, we do have everything that we need for the water. And we could go into the specific heat equation for water to see how much energy in this case is going to absorb. The mass is 150 grams. Specific heat capacity of liquid water 4.184 joules per gram per degree Celsius. Final temperature of the water 25.5 minus our initial 23. That's going to tell us here, come here, 25.5 minus 23 times 4.184 and times 150. Going to tell us that this water here is going to gain basically 1,569 joules of energy. Once again, it's a positive number, as we would expect, since the water is the one absorbing the energy from the metal. Any questions so far? With that being said, that also allows us now to figure out how much energy was lost by the metal, as it is really the only thing supplying the energy to the water. And again, we can use that relationship of Q of the metal is equal to minus Q of the water. And that would mean for our metal, it's going to be a negative 1569 joules. So we now have the Q of the metal from just following what's happening with the water. And now we have everything we need for the metal part of the calculation. So going back into our specific heat equation with the metal. And again, here we're going to solve for S, which is Q of the metal divided by M delta T. Pop it in our number there, negative 1569 joules divided by the mass of the metal, which is 110 grams. Final temperature of the metal, 25.5 minus our initial 55.5 degrees Celsius. Once again, that is going to give us a negative number, which is going to take care of the other negative that we got going on there. And that's going to get us a 1569 divided by a 110 and divided by a 25.5 minus 55.5. And it looks like we will end up with 0.48 joules per gram per degree Celsius, as none of the units, again, cancel out in this case. Any questions on that? So again, like I said, it's a very common sort of process. It's kind of using water to sort of figure out what's going on, as we always have a specific heat capacity of liquid water. And frankly, like I said, you could do these type of experiments simply with a couple coffee cups that are nicely insulated, and a thermometer is all you pretty much need. Any questions on that there? All right. As I talked about before, there is obviously a nutritional calorie that's sometimes referred to. Again, that does have a capital C. And remember that that is basically 1,000 of the little calories, as we talked about earlier, are 1 kilocalorie. And a calorimeter is a device that's used to measure calories in food. This is sometimes referred to as a bomb calorimeter because you got water in a very insulated container, got some wires and some oxygens. You put your chocolate chip cookie down there and you ignite it and sets your chocolate chip cookie on fire. And you basically just follow the change in the temperature of the water because as it's releasing its energy into the water, and then basically you could just do a simple calculation like we just did to figure out how many calories the water absorbed. And that would be how many calories that you could turn into nutritional calories that the cookie released in that case. And you could basically figure it out. Now, sometimes the calorimeter itself has its own sort of specific heat or capacity for the calorimeter. We're not going to get too much into that in this class, but sometimes it actually does have its own sort of capacity. Also, the three types of foods do have a caloric food value. If you ever looked on a nutrition label on food, usually you could see these three sort of groups on the label: carbohydrates, fats, and proteins. And they each have a caloric value associated with it. Carbohydrates and proteins are 4 kilocalories per gram, and fats are 9 kilocalories per gram. So, how they get to those sort of values you see on the table is they use these sort of caloric values and add up how many grams of carbohydrates there is, how many grams of fat, how many grams of protein, and basically just multiply each one by this caloric value, add them all together, and that gives you how many nutritional calories a substance has. Usually on those labels, they like to round down usually for the total calories when they do it. Now, in a laboratory like you'll do next week, like I said before, we could do constant pressure calorimetry, and it's sometimes called coffee cup calorimetry because typically we just use these foam coffee cups, which I guess now you can't get anymore around here. And basically, it's so well insulated that you could do reactions in this. You put a little lid on it, and basically, like I said, all you need is basically a thermometer to go in there, and you can just follow the change in the temperature, what's happening in there. You could do some experiment like you will do, and like we looked at in these examples, where you take a hot piece of metal and put it into the water and figure out something like the specific heat capacity of the metal. You could also just do actual chemical reactions in coffee cups as well. You could take an acid and a base, mix them together, and let it do its thing. You take some zinc and some hydrochloric acid, do like a single replacement reaction, and just monitor the change in the temperature of the solution. Because most aqueous solutions are water-based and a majority of the solution is water, you could use just a specific heat capacity a lot of times of just liquid water, even though it's kind of a solution. And you could do the same type of calculation to figure out how much heat is either gained or released by that reaction. Now, one of the things when you do that at constant pressure, which is typically what you do in the lab, the pressure doesn't change all that much. When you actually calculate Q under those conditions, you are calculating the change in enthalpy. So you could actually calculate the change in enthalpy for a reaction by simply a couple of coffee cups and a thermometer, and you're good to go. And you could actually calculate it very simply by just, again, following those change in temperatures. You can figure out how much, say, kilojoules per mole. If you know how many grams you started with, convert those to moles, you divide it, and you get how many energy per mole in that particular reaction you did. All right. The last thing we're going to talk about here in this chapter is what's known as Hess's Law. And Hess's Law is the idea that, again, energy is really a state function. And the idea of Hess's Law is a pretty simple one in a sense that not all reactions occur sort of in a one-step process. So when we look at a reaction like this overall reaction of like A plus B goes to E plus F, this may not occur in just a one-step sort of fashion. It may actually be a result of multiple steps happening, like A plus B goes to C plus D, and then like C plus D goes to E plus F. I know the alphabet nice. And we're going to add these together here. And just like we had any type of equations, like we did even with the equilibrium type of equations, things on opposite sides of the arrow that are the same will cancel out. So those would cancel. And that would leave us our overall sort of reaction that is taking place. Now, if each of these steps have a delta H value associated with it, um, what you would do, say that's 5 kilojoules and that is 10 kilojoules. To find the delta H of this reaction, you would essentially just add each of those together. 5 plus 10 would give us a grand total of 15 kilojoules of energy as a result of that. So with Hess's law, what you do is a lot of times if you have an overall reaction, you're looking to try to determine what is the delta H for that reaction or the change in enthalpy of that reaction. You can figure it out if you know sort of individual reactions that add up to that. Now, when we look at equations, there are certain things that when we manipulate an equation, which we may have to do in a Hess's law situation, how it affects the delta H. And it is different than how the K value is affected when we manipulate equilibrium reactions. So when we're using these type of reactions with energy, if we have a reaction such as this, and let's just say the delta H is 10 kilojoules. And let's just say, for example, we are doing this Hess's law sort of situation, but the way the reaction is written, we don't need it that way. We need to kind of reverse the reaction. And if we were to reverse the reaction in this case, we would end up with C plus D goes to A plus B. How that affects the delta H in this case is different, as I mentioned, than what we do with equilibrium. How it affects the delta H is we change the sign. This would be minus 10 kilojoules in this case. And that's because the way that we calculate delta H is products minus reactants. So when you reverse the reaction, your products become your reactants and your reactants become your products. And the only thing that changes is the sign. You still end up with the same number, just the sign changes. So if you ever come across a situation where you have to reverse a reaction like this, how the delta H changes is you change the sign. So if it was positive, it becomes negative. If it was negative, it becomes positive. Just also like equilibrium, we're manipulating those equations. Maybe there's a situation where you need two of A and not just one. So maybe you needed to take this equation and multiply it by 2. And if you multiply that equation by 2, you end up with 2A goes to 2B goes to 2C plus 2D. How that affects the delta H is we actually would multiply the delta H by the 2. And this guy would end up being 20 kilojoules of energy for his delta H value in this case. So we don't square it like we do with equilibrium. Here we multiply by the delta H. And lastly, if you needed to divide one of these reactions by a common number, so let's just say we wanted to take this reaction and we wanted to divide it by 2, that would return us to our original equation. And how we would affect the delta H is we would take 20 and divide it by 2, and we would be back to our 10 kilojoules. So these are very common ways that we manipulate these sort of equations with delta H values, and it happens a lot with Hess's law when you're doing these type of problems. If you need to reverse a reaction, change the sign of delta H. If you need to multiply by a common number, you multiply the delta H by that number. And if you need to divide by a common number, you divide the delta H by a common number. Any questions? All that there. So taking a look here, as I wrote over it there, let me get rid of it there. So if we were going to sort of add these two reactions together, again, the waters here in the gas phase would cancel out. And we would be left with H2 plus a half of O2 goes to H2O. And once again, in this case, we didn't manipulate these equations at all. So we would, again, just add the two delta H's together in this case, and that would get us to our minus 286, basically, kilojoules in this particular case. Any questions on that there? Okay. So let's take a look at this one here, and let's just say actually we wanted this equation instead. 2CO2 goes to 2C plus 2O2. We wanted a delta H of it. So why don't you give it a go? And we want to figure out the delta H using those guys down there. I'll do it too, and we'll hope it works out. If not, we'll just erase it, cut it out of the video. Nobody will hear it, ever. Let's see. Okay, so let's take a look. So when you're doing these type of problems, in this case, we have just two equations to deal with. Sometimes you may have three or four, or a bunch of them. Really what you want to do is just kind of keep it as simple as possible. So the best approach is really just to look at your desired equation here and just try to get everybody on the correct side. So here, obviously, we need CO2 on the left-hand side. This equation here is the only one that has CO2 in it, and it's on the right-hand side. So for sure, we do know we need to reverse that reaction. In addition, we don't need just one of them like it is in that equation. We actually need two of them. So in addition to reversing it, we also have to multiply it by 2. So that's what I'm going to do. I'm just going to rewrite the bottom equation there and reverse it first. And that will just move my products and reactants to the opposite side. And then I'm going to multiply it by 2. So I'll come across here and multiply it by 2. And obviously here, when I multiply that last guy by 2, that is going to end up being just 1 in this case. Now, because I did some manipulation here of this equation, I also got to keep track of the delta H, what happens to it. First off, the delta H in this case is going to change signs because I reversed the reaction. So instead of negative 283, it's going to become positive 283. then it is going to be multiplied by 2 because I multiplied the equation by 2 as well. And that's going to give us now for our new sort of equation, our delta H of 566 kilojoules. Any questions on that there? Next, I'm just going to kind of go this way, and I have carbon now on the right-hand side, and obviously here in the first equation, I have carbon on the left-hand side, so I do need to reverse that reaction as well. And in addition, I need 2 carbons, so once again, I also need to multiply it by 2 as well. So reversing the reaction, that'll put the CO on the left, that'll put my carbon and my oxygen on the right. I'm going to multiply by 2, which also will make my 1/2 into a 1 in this situation, I think, there, if I did that. How do we do there? Okay. And that means in my case of my delta H, I reversed it, so it becomes 110 kilojoules. And we also multiply it by 2, so we'll have 110 times 2. That's going to end up at 220 kilojoules. And if I didn't screw up here, we should end up now when we add these together with the equation we're looking for. So the 2 COs on both sides will cancel. Everybody on the left-hand side of the arrow stays there, so 2CO2. Everybody on the right-hand side of the arrow stays there, so 2C plus 1 and 1 make 2O2. So we did end up with the right equation, so that's good. That means the delta H of this guy is basically just going to be these two numbers added together. So 566 plus 220 going to give us, in this case, 566 plus 220, 786 kilojoules in this case. And this reaction would be endothermic in this case, as we did end up with a positive value here of delta H. Any questions on that there? All right, let's take a look at another one here. There we go. All right, so we're looking for the delta H of this reaction using the 2. I'm assuming maybe one of the answers are up there. Let's see what you come up with here. Okay, so let's take a look once again, just trying to get everybody to the right side. So I got SO2 here on the left. I do see SO2 in this equation, but it's on the right. So I do need to reverse that equation. Here I just need 1 SO2. So all I'm going to do with that equation is just reverse it around. And we'll end up with this. Because I reversed it, how that affects, again, the delta H here is we're just going to change the sign. So it'll become a positive 297 in this case. For our SO3, we need it on the right-hand side, which it is in the second equation, but we need just one of them. That means I do need to go through here basically and divide everybody by 2. And if I do that, I will end up with S plus 3 halves O2 goes to SO3. Once again, because I divided only, I'm going to take my delta H here, and we're going to keep the sign the same, but divided by 2 in this case. And that's going to get us 792 divided by 2, 396 negative. And once again, if I did this correctly, I should end up with the equation I'm looking for. S's are going to cancel. I have 102 and 3 halves. That's going to leave me, when this cancels out, a 1/2 O2 over here. And that will get me SO2 plus a half of O2. Gives me SO3. So I did build sort of the right equation here. That's good. And in this case, we're now going to just basically add these delta H's together. So 297 plus a negative 396, going to look like the delta H here. It looks like a negative 99 kilojoules in this case. And negative meaning it is going to be an exothermic type process happening here. Any questions on Hess's law? So basically just kind of build an equation from a bunch of other ones and just keep track of what you do to them so you could adjust the delta H's correctly. Then all you have to do at the end is just add up all the delta H's together, basically. Any questions on that there? All right, that should be, I think, chapter 7 on pace. So chapter 7 talked really about thermodynamics in terms of energy. We're going to now in this chapter talk about all the other thermodynamic sort of properties. Entropy, which, dare I say, gives us a new letter to look at, which is delta S. And free energy, which is also a new letter, delta G. And obviously what we just talked about there in the last chapter, our delta H will also find its way in here. And it wouldn't be a 200B class without our good friend K as well. So we'll eventually tie it back to the equilibrium constant in this shorter chapter. So we're going to talk about thermodynamics in this chapter. And really one of the things, as I said a little bit earlier, that thermodynamics really try to sort of determine is the idea of whether or not a reaction is spontaneous. Now, when people sort of hear spontaneous or this reaction is spontaneous, they oftentimes have the wrong indication of what that means. People associate spontaneous with I snap my fingers really quickly and it happens super fast. And that is not what spontaneous means in this case. What spontaneous means in this case, and in the case of thermodynamics, is it has really nothing to do with how fast or slow a reaction will take place. That is really what kinetics sort of studies. What thermodynamics studies in terms of spontaneity is whether or not a reaction will actually just occur. And if a reaction is spontaneous, it could occur really fast or it could take forever to occur, but it will eventually occur. So when we talk about a reaction being sort of spontaneous, what we're referring to is the idea of under these specific conditions, if you leave it long enough without any other help outside interference, this reaction should take place by itself. And again, that could occur really fast, it could occur really slow, could occur somewhere in between. So again, it has nothing really to do with how fast or slow a reaction takes place. So for example, here are some physical and chemical processes that we're sort of familiar with in terms of being spontaneous. Water runs downhill usually, right? It doesn't just automatically go uphill by itself. Sugar will dissolve. Obviously, ice will melt at above 0 degrees and freeze below it. As we just talked about, heat transfers from hot to cold. And iron exposed to oxygen with a little bit of moisture is really all you need for rust to sort of form as well. And again, like you think about the ice cube example, if you take an ice cube out, you just leave it there. You don't really have to do anything to that ice cube, right? It's going to spontaneously start to melt from the room temperature heat without you having to like put it on the stove or anything like that or put a fire under it. It's just going to happen, right? And you don't have to help it happen. And that's really the idea behind a reaction being spontaneous is there's really no outside factors helping it happen under the conditions this reaction takes place is all that you need for that reaction to take place. Clearly, if you're skiing downhill, that's a spontaneous process, right? You just need a little push down the hill. If you're going uphill, it's not going to happen unless you do something to help yourself up the hill, right? So that is definitely not a spontaneous process. And I imagine if you're skiing downhill, you probably don't want to see somebody skiing uphill. I would imagine it's not really what you're looking for. Here, in terms of gases, if we have a bunch of gas molecules on one side and a little kind of valve, if we open it, just spontaneously, these gas molecules are going to migrate over to the other side. But if we started with gas molecules on both sides, it is probably not going to happen that all these guys are going to decide by themselves to kind of go to the other side without any type of outside help to sort of encourage them to go to the other side, right? Maybe if you heated up this side, it would encourage them, but that is, again, not going to spontaneously head over to that side. So does a decrease in enthalpy mean that the reaction proceeds spontaneously? So when we talk about enthalpy, as we just did in the previous chapter, remember that if we have, again, a delta H that is negative, it's an exothermic process. And if we have a delta H that is positive, it is an endothermic process, heat being absorbed versus released with a negative. Here we have a couple reactions which are spontaneous: combustion reaction, formation of water. They're both negative here, and that is an exothermic process. The melting of ice, as I just mentioned, is a spontaneous process, and that is an endothermic process. And that is also an endothermic process, the making of a solution. So, what this tells us is we cannot look at delta H or the change in enthalpy or the energy change as like a factor of whether or not a reaction is going to be spontaneous or not, because as we can see here, we have some reactions that are exothermic that are spontaneous, and we also have some endothermic reactions that are spontaneous. So we cannot use delta H as really the sole measure of whether or not a reaction is spontaneous. What it says on the bottom there is exothermic reactions do favor spontaneity, and exothermic reactions do kind of favor being spontaneous because it just has a lot more energy sort of happening in that situation. That's all very favorable for a reaction to take place, but it doesn't necessarily guarantee it. It is possible, believe it or not, to have sort of an exothermic reaction that could technically be non-spontaneous and vice versa. So, what is one thing that we could use to help us understand whether or not a reaction is going to be spontaneous? We do want to look at another sort of thermodynamic value. And as I mentioned before, this is entropy. And entropy sounds very much like enthalpy, except it is entropy. And it has an abbreviation of S, or delta S. It is sometimes referred to as the change in entropy. And basically, entropy is the amount of randomness or disorder there is in a system. Entropy is slightly different than we normally sort of associate things. So normally we think, for example, with delta H, it's negative, things are happening when things are negative, and maybe when things are positive, it's not such a lot happening there because it's an endothermic type process. But actually, with entropy, the more order you have, the more organization you have, the more order you actually have a decrease in the change in entropy. And you actually end up with a negative value for entropy. And the more craziness you have and disorder that you have much more entropy happening. It's actually more of a positive value. So if you end up with a final state that actually increases the amount of craziness and disorder, you will actually end up with a more positive value for S. And if you end up with a situation at the end, say, of a reaction that you ended up with a lot more order happening, you will end up with a negative value for S. So it's kind of a little bit opposite of where you sort of think about negative and stuff like that. Now, one of the easiest ways to see sort of the difference in order is to look at things in different phases. Things in the solid state are very organized, right? Because they have less energy, they're packed in there pretty tight to one another. There's not a lot of movement happening or craziness happening. And that has a lot less entropy than, say, the liquid state, where they're still relatively close to each other, but they have a little bit more energy, right? So things are moving around a little bit more, and that's going to create a little bit more entropy than you did in the solid state. And then clearly, when you get to the gas state, everybody's flying around crazy, right? And that's a lot of disorder happening there, and you see a big jump in the entropy. So things in the gas state have a lot more entropy than things in the solid state or the liquid state. I think about it when we go through this chapter a lot of times, is like, especially with gas molecules, you got a lot of things flying in your face, right? That's a lot of disorder. Gas molecules, you got not so much flying around in your face, a little bit more order happening. And that's a good way to sort of think about it, as you go through it. So here, if we had basically ice going to liquid water, again, this is a physical change happening, and that's a solid. And obviously, as we go from ice to liquid water, we're creating a lot more disorder over here. And overall, here, our final state is more disordered than our original state. And we would expect our delta S in this case to be a more positive number when we calculate it. So if you in a reaction create, like we do here, a lot more disorder, when you do calculate delta S, you should expect it to be a positive number versus a negative number if you did the opposite. Now, disorder is related to probability, and a probable event is one where there are many ways in which it could happen. An improbable event is a way where there's only a few ways that it could happen. So a ordered state has a really low probability of occurring and a small entropy. A disordered state has a very high probability of occurring and a larger entropy. So, for example, if we needed to get out of this room with all the doors that are here, there's a pretty good chance we could get out of this room. We could take that door or that door, I suppose. But if we didn't have those doors and we had just one small window up there in the top corner, there's a smaller chance that we would all get out of here, right? If we needed to exit this room. Happy thoughts here as we close out the day. So again, less ways to get out of the room, a lot less of a chance that we could do that. When you have a ordered state and you do something correctly, there's only a few ways you could do something correctly, as people tell you, right? There's only one way to do it right? But there's a lot of ways you could screw it up, right? So there's a very high probability that you might screw something up, right? And there could be a lot more entropy and disorder that could happen with that. So when we talk about entropy, there is with this equation here, which is what is referred to as the Boltzmann constant, or the Boltzmann equation. And this is the entropy. And this is the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. And W is the number of microstates, actually. And it's just sort of the different ways in which you can sort of accomplish something. So if we were looking here at these circles, and this was kind of like a carnival game, I guess, if you want to throw the balls and try to get them all to one side. If you want to get all four of them on one side versus the other, there's really only kind of one way you could do that. You could either put them all on the left-hand side or put them all on the right-hand side, and that gives us one microstate. If you wanted to win the small prize at the carnival, you just need to get one on one side and three on the other. Then there is four different sort of ways that you could accomplish that. And if you want to just go and get something for trying there, you get two on each side. There's 6 different ways that you could accomplish that. So the more probable event is probably easier just to try to get 2 on each side, right? More ways that you could do that rather than having to try to get them all on one side. It's probably going to be a little less probable. If we were to kind of pop those into the Boltzmann equation here, and since the Boltzmann K there is a constant, if we did our microstate of 1, that would give us S is equal to K natural log of 1. Natural log of 1 is 0. So you basically have very small entropy there. If you did the Boltzmann for the 6 there, natural log of 6, and we'll just take the Boltzmann constant out of it. Natural log of 6 here is going to give us like a 1.79. And that's obviously going to give us a much higher positive entropy in this case, and much more ways of accomplishing that. So again, the more ways that you can do something, the more probable that's going to happen. The less ways that you can accomplish something, the less probable it's going to happen, is going to have lower entropy. Here again are all processes that lead to an increase in the entropy of the system. As we talked about before, as we go from solid to liquid, we got a lot more movement of the molecules, a lot more energy, definitely as we go from liquid to solid. When you make a solution, that is increasing the disorder for everybody. The solute, like an ionic solute, is organized in a very organized way. And also, so is the solvent. So something like water, they are hydrogen bonded to each other in a very organized sort of fashion. In order to get everybody to dissolve, you got to break apart those water-water interactions, got to break apart like these salt interactions, and now you got a jumbled mess of everything there, and an increase in the amount of disorder that's happening as you got ions floating around all over the solution. and that's going to increase it. One of the ways as well that we increase the disorder is increasing the temperature. So if this is our guy at temperature 1 and this is our guy at temperature 2, and temperature 2 is hotter, they're going to have a lot more energy, and a lot more energy is going to get things moving a lot more, and that's going to cause a lot more disorder to occur. So increasing the temperature increases the energy, and that increases the disorder that can happen. All right, so for each of these, take a moment and decide, is the entropy of the system increasing or decreasing for each of these situations? So condensing water vapor, so condensation is going from gas back to liquid. So we're going from a state where everybody's flying around to a state where they have now condensed back down into the liquid state. That is definitely creating a lot more order in this case, a lot less disorder in this case. And because of that, we would expect the delta S here to end up being a negative number as the entropy is decreasing in this case. We're becoming more ordered. Any questions on that there? Forming a sucrose crystal from a supersaturated solution, a crystal is a very organized sort of situation. And that would mean that we're definitely creating a lot more order in this case. Again, supersaturated solution is actually a liquid form before it basically breaks out into a solid. And again, creating the order there is going to cause our delta S to be more negative, decreasing the amount of entropy in this case. Any questions on that there? Heating hydrogen from 60 to 80. Again, when we increase the temperature here, those gas molecules should gain a lot more energy, which means they're going to be flying around a lot more crazier in front of your face. And that's going to create a lot more disorder that's happening here. And that increase in disorder will actually mean our delta S should end up becoming more positive as a result of that. And our entropy should be increasing in this case. And lastly here, sublimation, hopefully you know, is solid directly to gas. So we're taking something from the solid state directly to the gas state. And that clearly is going to go for something that's much more ordered in the solid state to something that is much more disordered and flying around crazily there in the gas state. And that should increase the disorder, and we should end up with a delta S as positive and an increase in the entropy. Any questions on